Hello everyone, myself Kavi Pranesh. Today I'm going to present a topic on plasma doping. Here, this is a small content about the topic under various subheadings which will be covered in this presentation. Now, what is plasma doping and why do we require plasma doping? Plasma doping is a process used in semiconductor manufacturing to introduce dopants into semiconductor materials. Plasma doping is also called as PLAD is a productized implant solution for high dose, high throughput applications such as dual polygate counter doping or contact resistance reductions. Ion implantation is the preferred approach for junction formation due to its precise control of dopant depth and dose. Arsenic and phosphorus dopants are used at many process steps to dope crystalline silicon and other substrates in advanced memory devices. The conventional thermal processing is used to recover crystalline silicon amorphization but may be subjected to residual defects. Heating the substrate during implantation is a novel technique which is followed in the industry, which has been adopted in advanced semiconductor devices to limit the amorphous region and allow for complete recrystallization in subsequent thermal processes. Unlike traditional ion implantation, which uses high energy ions, plasma doping employs plasma to create reactive species that modify the properties of semiconductor materials. These are the few reasons why we prefer plasma doping over ion implantation. The plasma doping process involves three key steps: plasma generation, plasma transport, and plasma surface interactions. The figure shows the chamber consists of radiofrequency ion source generating plasma which impinges on a wafer that is electrostatically clamped to a plate. The plate and wafer system are then biased at negative potential from 100 volt to 12 kilovolts to extract ions. These implants are typically done with the platen at room temperature or slightly elevated temperatures up to 70 degrees Celsius. So, the first step is the plasma generation. In this step, the plasma is generated by introducing a gas into a chamber and ionizing it through the application of an electric field. This ionization process gives rise to a plasma containing ions, electrons, and neutral species. The plasma is then directed towards the semiconductor material that requires doping. Now, once it's generated, the plasma is transported to the semiconductor material through a chamber. The plasma species are guided towards the substrate by the electric field present within the chamber. Careful control of gas flow rate and pressure ensures optimal plasma density, which is crucial for effective doping. So this process is called plasma transport. The last one, the plasma surface interactions. So once upon reaching the semiconductor surface, the plasma undergoes interactions that modify the material's properties. These interactions can involve the penetration of plasma species into the surface, creating defects that facilitate dopant diffusions. Alternatively, the plasma can form a thin layer on the surface, allowing dopants to diffuse into the material through this layer. There are two types of implementation. The first one is the gas source plasma doping. Is usually performed in a plasma diluted by helium sustained by an electron cyclotron or radio frequency plasma source. The aim of dilution is to control the implantation rate and toxic dopant species. The below image shows the elements used for solid source plasma doping, which is ammonia and graphene growth on the substrates. Plasma doping offers numerous advantages over traditional ion implantation techniques. Firstly, it enhances dopant activation, resulting in improved device performance. Secondly, it provides higher throughput, enabling for faster processing times. Additionally, plasma doping is more cost effective than ion implantation as it eliminates the need for expensive equipment and can be performed at atmospheric pressure. Lastly, it reduces crystal damage due to the use of lower energy ions, preserving the integrity of the semiconductor material. While plasma doping offers numerous advantages, it does present some challenges. For instance, the creation of defects and impurities during the process can affect device performance. Additionally, precise control of plasma parameter is crucial for optimal doping results. The applications of plasma doping span various semiconductor devices. In CMOS devices, plasma doping plays a vital role in improving transistor performance, leading to faster and more efficient integrated circuits. Power devices benefits from plasma doping by enhancing conductivity and reducing power consumption, making them ideal for energy efficient systems. Furthermore, plasma doping finds applications in memory devices, increasing storage capacity and reducing the access time. As we saw, plasma doping is a powerful technique used in semiconductor manufacturing to introduce dopants into semiconductor materials. By using plasma to modify the properties of the material, manufacturers can improve device performance, reduce power consumption, and increase storage capacity. Though plasma doping has some challenges that need to be addressed, such as creating defects and impurities, it offers several advantages over traditional ion implantations, like improved dopant activation, higher throughput, lower cost, and reduced crystal damage. Overall, plasma doping is a promising technique that has potential to revolutionize the semiconductor industry, and further research is needed to address its challenges and improve its applications. Thank you.